Okay, picking up from where we left off, the next thing we're going to do is we're going to we're going to talk about how the K function or L function behaves with an inhomogeneous Poisson process. So, jumping back to the notes here. Actually, let's not do the notes first. Let's jump to R. Okay, so just below the section of code that we just ran, starting at about line 307, what we're going to do is we're going to generate an inhomogeneous Poisson process, and the this is that example that is linear in the X location and linear in the Y location. I've done it on a very large window from 0 to 10, which gives us enough range in X and Y to really see the inhomogeneity of the Poisson process. And so this should be a slam dunk example of it. Clearly we have different intensity up here in the upper right than we do in the lower left. And this is probably unrealistic, but it allows us to kind of get a feel for how this K function is going to behave, or the L function. So in line 316, I'm going to run the L function for this data, and I'm going to plot it. And here's what we get. And what I want you to notice is that the behavior here appears to be different than what we were seeing for, in particular, the Neyman-Scott process. But so for both the Strauss process and the Neyman-Scott, we saw deviations from complete spatial randomness, but that deviation appeared to be pretty localized. And focusing on the Neyman-Scott, which had aggregated behavior, what we saw was that the L function indicated that the observed number of points at small radiuses was greater than we would expect under complete spatial randomness. But it pretty rapidly corrected itself. The L function for an inhomogeneous Poisson process, it isn't always going to behave this way. But with kind of this slowly varying trend like we have in this particular example, it's kind of analogous in a way to having a trend surface for a geostatistical process. So we saw that when the process was not stationary, when we had a mean surface, a trend in the mean, the tool we had to analyze spatial behavior in geostatistics was the variogram, and we saw that the variogram behaved in a certain way. It tended to wander off because those differences became larger. The difference in the z values became larger with increased distance. There wasn't for a stationary process, when you get to a certain distance, you expect those distances to be no longer correlated, but that difference between the z values when you had a mean trend just continue to increase. Maybe we have something kind of analogous here. So again, we have a slowly varying trend in our intensity here. And what we see in our L function is different than the Neyman-Scott, where there was kind of a dramatic and short-term distance. What we see here is kind of a persistent deviation from what we would expect under complete spatial randomness. Now, again, in the upper right, we see that it averages, once you get a large enough radius, it tends to average out enough that the observed number of points is about what we would expect under complete spatial randomness. But at short distances, we do get this kind of prolonged, or this persistent aggregated indicator that of aggregated behavior, or indicator that the observed number of points is larger than we would expect under complete spatial randomness. Now, where that's coming from is a little harder to see, in this plot, but what's happening is it's taking every circle, it's counting the number of points within a distance, and basically because there are more circles, more events to choose from up here than down here, we're getting it's going to indicate that it's finding more points, and the average number of points within a given radius is greater than it would expect if we had complete spatial randomness. So it's a subtle difference. It's not the K function is not dramatically different, but the fact that it's persistent might be some indication that we have something quite different than a name and Scott process. And obviously the realization is quite different than a name and Scott process. Okay, with that, let's jump back to the notes for a minute. And so this is my cartoon of trying to show that the L function of an inhomogeneous Poisson process has this more persistent behavior than something with a name and Scott or a Poisson cluster process. Posing the question, should the K function really even be applied to data with a non-homogeneous intensity? And the answer is really no. The K function is designed to study that second order intensity. What we showed sort of mathematically was that the K function can be related to that lambda2 value, that second order intensity. And you can sort of, just like in geostatistics, you can really only start to characterize that second order behavior, the variogram or the covariance function, after you've accounted for the first order behavior in the mean. The same is true here, and to quote Schabenberger and Gottway, they say on page 114, the assumption of stationarity on which the K function is based precludes its use for inhomogeneous Poisson processes. So what they're saying is, if you have an inhomogeneous Poisson process, don't use the K function. Well, that's easily enough said, but how do you know that you've got an inhomogeneous Poisson process before you start to investigate it? So I think it's quite reasonable to imagine somebody collecting a map data set, running a K function, trying to interpret it, and what the takeaway message should be is, if you're getting this kind of behavior, then perhaps what you have is inhomogeneity in the intensity, and you need to think about accounting for that somehow. So let's see, I think I've said this bit of the notes. And I've said, it is kind of analogous to fitting a variogram with a trend. So takeaway message is the K function is designed to study second order intensity. If applied to an inhomogeneous Poisson process, it can, in certain circumstances, in this trend example, give some indication that you have inhomogeneity. But I think looking at, if you have the mapped data, just making a plot also could give you some indication. Is it hard? Is it difficult to choose between inhomogeneous intensity and second order behavior clustering? Absolutely, particularly if you think of, say, our model for the Cox process, our log Gaussian Cox process, where you throw down a geostatistical model, you can imagine a realization of a Gaussian process would have maybe a localized maximum. Think of a hump. Well, then when you apply your inhomogeneous Poisson process, you're going to get a higher number of events at that near that location, and so it might look a lot like a name and Scott. So starting with data, it is absolutely difficult to try and choose between first order behavior and second order behavior. And really what we have to do as the experts in the room is talk with people, understand what might be driving it, what kind of model makes more sense for the data, and then proceed forward. Okay. So how can one, we talked about performing hypothesis tests with quadrat data or with distance data, distance sampling, the Clark and Evans nearest neighbor function. How do you do hypothesis testing with the K or the L function? Well, what the way that I'm most familiar, the way it seems to be done is to construct envelopes. So the hypothesis testing, of course, you start with a null hypothesis, and then you say, does the data deviate enough from what my statistics would look like if the null hypothesis were true? We're going to apply that general notion to the K function or the L function. What we're going to do is we're going to generate realizations of the L function under our null hypothesis, presumably of complete spatial randomness. That will give us an envelope of realizations. It's sort of like it has a permutation test feel. Well, not really permutation because we're not resampling the data, but what we're going to do is just generate K functions under complete spatial randomness, make an envelope of those K functions, see how our observed K function deviates from that envelope, or is it, within the what would be expected under complete spatial randomness. So again, let's jump to R. And there's really a tool right in STAT623 to do this. So let's start with a Strauss process. Here's our Strauss process. It exhibits some regular behavior. It's really hard for me to tell whether that deviation from complete spatial randomness is significant or not. Is this within the what could be expected if there was no inhibition in the generating process? So you can, what we have here is the K function, not the L function. The blue line corresponds to what we would expect from complete spatial randomness. The black is what we're observing. And then with this command envelope, what it's going to do is it's going to generate an envelope. The Strauss is saying, this is just what I named my particular realization. The envelope tool is necessarily going to assume complete spatial randomness. And so if we plot it, here is the here are an envelope of K functions under complete spatial randomness. Notice that our realization of the Strauss process is not so far from complete spatial randomness that we would reject the null hypothesis. So even though there's some indication of regular behavior, it's not so strong that we would reject if we were in that hypothesis testing framework or state of mind. You can also do the L function. So before was the K function, here's the L function. To do the envelope, I just have to use the L function. So here is that envelope. Again, we're seeing that we would fail to reject the null hypothesis of complete spatial randomness. Okay. There's that issue of kind of, do you is your envelope pointwise or is it global? And you can do a global test. I think a pointwise test makes more sense to me, but there is a tag to make kind of a global type of rejection region rather than a pointwise rejection region. Here's our Strauss process again. I guess I want to plot L out. Let me try. Okay, so here is our Strauss process. I guess my window is a little bit big. And we talked about how we failed to reject the null hypothesis under complete spatial randomness. But if you think about this procedure of generating an envelope, how does it work? Well, behind the scenes, what it's doing is it's generating a random field according to complete spatial randomness, calculating the L function, storing it, doing that repeatedly over and over and over again, and then it generates an envelope from those realized L functions from complete spatial randomness. Well, there's no reason that we can't do that with a different null hypothesis. We could have a null hypothesis of a Strauss process. And we could see if there's evidence to reject that null hypothesis. And so notice that in line 340, I'm telling it, oh, let's assume that our null hypothesis is that this data comes from a Strauss process. Is there enough evidence to reject that? So I'm going to build the envelope around the Strauss process. Here's that envelope. You see the envelope has a different characteristic because it seems to be, it has that regular behavior that it's occurring less than the 45-degree line. The red would be the mean of those realizations, and so this is what we would expect. And so of course, the envelope is generated from the same type of process that generated our one realization. So not surprisingly, we fail to reject, and this envelope seems to capture that behavior. Okay, so that wraps up our discussion of the K and the L function. We're going to return to talking about inhomogeneous Poisson processes. And what we want to do next is estimate that underlying intensity function. So that is where we will go from here on the next recording.